Hello everyone, and before we get going I want to say thanks for completing your assignment 2 online there. Got a lot of good tips for the preparation of the notes, so thanks for your thoughts on that. What I'm doing for all you AV nerds out there is I've turned my camera on to basically manual mode, so I've manually set the shutter speed essentially, and the aperture and the ISO, so I get a nice bright image. Hopefully you can see on the page it's nice and bright. And also I've moved over to manual focus, so the camera is focused actually on the plane of the page. So when I move my hand in front, maybe it seems a little bit out of focus perhaps, but that's good because I want the page to be in focus, not it autofocus onto my hand, which makes no sense, right? Okay, and also I did have one comment about the audio being, I think, heavy on one of the channels. Yeah, I noticed that. That was good. So what I've done, I've actually purchased a different microphone, and I'm using that right now. And hopefully it's even on both channels. I've actually set the microphone to be a manual kind of leveling. So one person mentioned the microphone's a little quiet. I've got I've got it the max I can for my normal voice without clipping. Okay, so this is as good as the microphone gets, I think. Okay, if you've still got problems with any of this stuff, if it's not bright enough, if the microphone's too, not loud enough, or anything like that, let me know, and see if there's anything else I can do. All right, so rant over. So let's talk about chemical bonding and periodic trends. We're nearly at the end of the syllabus, so today, as I'm doing this, it's the 29th. So if you have this done by the first week of May, you're on track to finish the syllabus in good time. Okay, I'll give you time to review as well. Okay, remember in the last week of class, and it's been extended by a week, remember, I think it goes through the 15th now. In the last week of class, I'll assign you that last exam, just like the first midterm in terms of score, 150, and just covering the material we've done since that first midterm. So that hopefully brings you up to speed. Distracted a little bit from the, from the video, but here we go. So chemical bonding and periodic trends. Well, what are we going to talk about? We're going to talk about the kind of the details of chemical bonding a little bit, okay? So in very, very simple terms, what is a chemical bond? In very simple terms, it's very much a force that holds two atoms together. So nice and easy, right? That's the very simple definition of what a chemical bond is. It's a force that holds two atoms together. And so far, we've actually looked at the two simple types. We looked at covalent and ionic, right? Now, it turns out that covalent and ionic are two kind of extreme versions of bonding. Ionic, of course, is where electrons are stolen and ions are created. Ions of different charge attract and stick. Okay, and then covalent, it's like shaking hands. They share electrons, okay? So those are two extreme kinds of bonding. As we'll see, most things actually lie in the middle, somewhere between ionic and covalent. So in this packet, we'll learn to see, hey, what kind of bonding do these two atoms have when stuck together? And we'll do that based on an electronegativity difference. Remember, ionic form because of a big difference in electronegativity or electron stealing strength. Covalent's very close in terms of strength, so they're pulling with equal force, if that makes sense. So if we look at a very generic ionic bond first, so a large difference, we'll understand what a large difference is with numbers in a little bit. But a big difference in electron stealing strength, electronegativity, we see a metal which is very low electronegativity, okay? And there's usually one, maybe two electrons on the outside there. And you bump it into a non-metal, which usually have, this is, for example, sodium chloride, which we've done before, okay? We have a non-metal. That's a high, I have to excuse my pen here, high electronegativity. Okay, what happens is you bump these together, and of course the electron is transferred. That's the process of ionization, and we turn into metal plus. Let me put it in a square bracket. You see that with the Lewis symbols, don't you? And then X minus. I'll switch pens. I came prepared with an extra pen. There we go. All right. So there we go. So if we look at lithium fluoride as a kind of a more practical example, we've seen this before. Okay, so lithium, let's do its complete dot diagram. 2 on the inside, 1 on the outside. Bumps into fluorine. I'll do crosses for fluorine. Now remember, we did this one before, atoms can twist and turn in space. So, you can twist this around so it works better, but here it's, ionic, so it's not so bad. If you like, column 7, 7 on the outside, a spot for 1 more. Column 1 on the outside, room for 7 more if it needs it, right? But remember, this is low strength, this is high strength. Turns out fluorine is the strongest electronegativity in the periodic table. It's the strongest, right? Yet, it only steals 1 electron. Not 3, not 4, not 2, but 1. If it's the strongest, why does it only take 1 when it can take so many more? It's because it only needs 1 to get that full outer layer. And if you look what's left when we finish, talked about this in the previous packets. Lithium is now isoelectronic, lithium plus ion. It's a plus because it's 1 less electron. It's now isoelectronic, and that should be plus, just correct that. And that's isoelectronic with helium, right? Okay. Whereas fluoride now, fluorine becomes fluoride when we make ions. Got 1 more electron. Boom, there it is. That's isoelectronic with neon, which has that 8 on the outside in the second layer. Okay, so we've obeyed the rules of valency, if you like. We've got full outer layers. Fluoride makes a -1, as do all column 7s, because they got 1 spare spot to park an electron. All group 1s make +1, because they got 1 on the outside that's easily removed. Okay, now remember, fundamentally that happens because lithium is weak and fluorine is strong. Okay, all right, now, moving on from there, flip over the page here, okay. So, recall that strength, electron stealing strength is called electronegativity, which I've been calling En, right? So electronegativity is En. This is probably my favorite slide of all time, right? Okay, so it shows you the diagonal trend in the periodic table as a function of height, all right? So bottom left is the weakest, that's cesium. Top right is the strongest, that's fluorine. No noble gases, because I've already got full layers. This only applies to atoms that are bonded, okay? So I guess theoretically they are further to the right, and helium particularly is further to the top right, but they're not stronger because they've already got full layers. So it only applies electronegativity to things without full layers, okay? So weak to strong, and we see that classic diagonal trend. If I draw this, it's my periodic table, that's the lowest, that's the highest, okay? That's why this area here, and I keep pointing to it in class, that kind of diagonal step separates the weak from the strong. It also separates metals from non-metals, conductors from insulators. So that line in the periodic table right there separates weak from strong. Okay, so these are your classic non-metals, they're strong. Metals, they're weak. Ionic bond between the two of these stuck together, we've said in the past, make covalent. Okay, so as we mentioned, covalent bonds, both from the top right. Small difference or no difference in electronegativity. No one wins a tug of war. It's a tie essentially. Well, it's a true tie for elements, which we'll talk about in a second. But hey, if they're close, similar strength, all large, all similar, no one wins, no one loses. It's covalent. Okay, and we've seen this before, so let's talk about a couple of quick examples. So if I had, for example, hydrogen, okay, and I'll flip it kind of on its side a little bit. So there's hydrogen and there's another hydrogen, right? If I push them together, coalescing, what do I make? Well, those outside layers overlap and I get a covalent bond, and that's what we wrote as a stick before, right? So that shared pair is a stick in our Lewis studies, right? If I do fluorine, just do the outsides of fluorine. Okay, so fluorine is column 7, I'll go anti-clockwise for this one, that's okay, remember? So if you like, I've got a space right there. I got my other one here. This time I'll go traditionally clockwise and then I'll go back again. There we go. Space right there. That can go in there. That can go in there. And now this is exactly what we did with our easy Lewis, right? So we're just kind of showing you that again. Crosses and dots just to show you whose electrons belong to who. Remember that thing there is a shared pair, right? In some books, a line equals a pair like that. They actually draw the shared pair, but in our class we like the line for the shared pair. Okay. Now remember, of course, that this all comes from the fact that these guys want a full outer layer. You know, when they overlap, that looks like neon because that's a shared pair. That looks like neon because it's a shared pair. That looks like helium because it's a shared pair. That's probably the better way to do it. Remember, if I drew it as dots, that would be 2 dots there, wouldn't it? So 8 on the outside, 8 on the outside, 2 and 2. Hydrogen's row 1 looks like helium. Fluorine's row 2 looks like neon. All right, so that's kind of almost like a refresher, isn't it, right? But as I mentioned, covalent, when they're perfectly shared, pair of electrons, and ionic, where it's a complete loss and gain, okay, two extremes, okay, either they're perfectly shared or 100% stolen, right? Turns out that things which have both nonmetals, for example, oxygen and hydrogen, say, okay, two nonmetals, both on the top right, with a reasonable difference in electronegativity, have both characteristics. So they're shared, yes, because they're both nonmetals, but hey, one's slightly stronger than the other, so it kind of pulls the electrons a little bit towards itself. And that creates a slight separation of charge, and it's called a polar covalent bond. So think of polar covalent bonds as a mixture between ionic and covalent, okay? So things that aren't perfectly shared, like elements like H2 or F2, and things that aren't ionic, like metals and nonmetals. So for example, HO, HCl, things like that. Things with a big difference, but they're both technically top right, okay? So when we have that situation, the atoms involved form a polar covalent bond, okay? So they're got to be both nonmetals. So if we go back to the old periodic table. And remember, I've kind of included, if I do that, okay, hydrogen is included in this, right? It's part of the yellow group, right? So anything yellow, if you like, which is kind of the weaker ones, with anything kind of orange, which is stronger, will make a really good polar covalent bond, okay? If it's identical, F with F, hey, no one wins identical strength, right? All elements are, if they're up here, molecular and purely covalent. But if it's a difference of electronegativity, yeah, it's covalent, but it's going to be polar. All right, let's see that in action. So if we look over here, these are electron density maps. So someone has actually gone out, set this up, and solved the Schrodinger equation for hydrogen fluoride, HF, and water, H2O. Okay. Now, it kind of looks like a pair, doesn't it? Right? Okay. Now, the more bulbous end, if you think about it, the electron is going to be, they've color-coded electron density as red, like hot, where there's lots of electrons, and blue, like cold, where there's not many. But you can kind of see from the shape, too. Obviously, there's more electrons down in this bulbous end than there is up here. It looks like a pair, doesn't it, right? So it's not an even spread. There's more down here than there is up here. So of those two atoms, who's pulling the hardest, right? Who's pulling the hardest? Well, it's going to be fluorine, isn't it? So if I nip down here now, this is kind of a follow-on. If I sketch HF, just like this, it's going to be F down here and H up here. Because what's going to happen, the electrons are going to be pulled a little bit that way. So instead of being instead of being right in the middle, they're pulled that way. And we call that a polar covalent bond. So that ends a little bit minus and that ends a little bit plus. Think about it a bit like a magnet with a north and the south end, but when we say polar magnetic dipoles, right, north and south magnets, this is an electric dipole, plus and minus, right? Okay, so kind of an equivalent. So the electrons are pulled a little bit away from center. You know, maybe if I drew them, they'd be like here or something. They've been pulled off their center mark slightly down towards fluorine because it's pulling stronger, because it's more electronegative, right? And that results in this kind of electron distribution. So it's, most of the electrons are down here, less are up here. That makes sense. If I kind of draw on top, you wouldn't do this on a test, but I'll just show you kind of the superimposed electron density there. Okay, now that's called a polar covalent bond. There's a separation of charge, poles, dipoles, right? So north and south, plus and minus. Okay, so this molecule is said to have a dipole, and we can kind of draw it if you take any physics the plus end and the minus end. Okay, like that. So that's a symbol that represents an electric dipole. All right, so give it a shot now for water, right? So here's water. Water's kind of interesting, one of the most interesting molecules out there in my opinion, right? So remember kind of orangey red's kind of hot, that's where the electrons are, kind of cold is blue. Think about how that's put together and think, well, which one is more electronegative, oxygen or hydrogen? Well, it's going to be oxygen. Oxygen is actually number two strength compared to fluorine, right? Hydrogen's weaker, so the electrons will migrate a little bit towards oxygen, so that would mean oxygen's at the top. So we got that kind of situation. Leave that up for you, right? Okay. Electrons are pulled that way. So this is a little bit minus. That's a little bit plus. That's a little bit plus. And that's kind of what we see with the map. Okay. Now this one, it's interesting. We'll talk more about it later. Okay. But the minus end is going to be this end and the plus end is going to be down here. And what we get is we get two dipoles. All right. We get that one and that one. Those are those two bonds, right? But when you do some kind of combination, they both have a component going up and they kind of cancel going sideways. So what we get is a net dipole. We get a net dipole that goes through the symmetric center of that molecule. So oftentimes we draw water molecules like that, okay? That's the oxygen end, which is a little bit minus. Delta means minus and delta minus, delta plus. Okay, so we saw that on one of my other favorite slides, the one with the tractors and trailers, if you remember how ions go into solution. That was my analogy. All right. So hopefully that explains polar covalent. If it's two, here's the trick. Here's the trick. I'll say it. Two non-identical, so it can't be an element because that would be identical. Two non-identical non-metals equals polar covalent, PC, polar covalent, where you have this kind of separation of charge, a plus and minus end of the bond. Okay. All right. Now it turns out electronegativity is unknown for all atoms, okay? So it's not a great picture, I know, you can barely see the numbers, but if you've got it in front of you, or hopefully if you're sitting in front of a big monitor, you can see the numbers, okay? So francium down here is 0.7, that's the weakest. Fluorine, we say 4.0, but it's actually 3.98, okay? And you know, the trend is low to high, and it matches the classic map we saw before, okay? So low to high, all right? Now, what you can do, if you think about it, the difference in strength, and we're talking about discussion here, the difference in strength determines the kind of bonding. Okay, if it's the big difference in strength, weakest with strongest, it's definitely going to be ionic. If it's any of the two that are the same, it can be fluorine with fluorine, nitrogen with nitrogen, hydrogen with hydrogen, doesn't matter, they're pulling with the same strength, so it's a perfect tie. So all molecular elements have covalent bonds which are perfectly shared pairs right in the middle. Okay, so that's what we've got so far. And then if I have things from the top right with a reasonable difference in strength, I'm going to get that kind of combination of the two, a polar covalent bond, a technically shared pair which is drifted further to the more electronegative thing. Now, when we go back to the numbers, do you think electronegativity values are determined experimentally or calculated? Well, look at the numbers. It runs 0.7 to 4. Do you think it's normal to kind of measure something in a nice range like that? It's like almost like a GPA, right? You don't have a 1 times 10 to the 16 GPA, right? You have between, 1 and 5 or whatever it is, right? Okay, so these are actually calculated, okay, calculated values. And later in the packet, we'll kind of look at things from which they are calculated, okay? And all the things we look at will follow that same bottom left or top right trend, okay? So lowest to highest electronegativity values which are calculated, okay? And they run from 0.7, which is the weakest, up to 4.0, which is the strongest, okay? All right. Now, we said a big difference was ionic and a small difference was covalent, right? Okay. How can you work out a difference? Well, if I said to you, what's the difference between 4 and 3, just subtract the numbers, right? So that's the difference, obviously, right? So if I want to work out the difference between the strongest and the weakest, okay, so for example, CF CS equals 0.7, and just for easy math, I say fluorine equals 4.0. Just subtract the big from the small. Delta equals 4 minus 0.7, 3.3. So that's the difference, right? That's a big number, a big difference. That's the biggest it could ever be if you think about it. So the biggest ever difference is the biggest number minus the smallest number, which is 3.3. So anything in that kind of range has to be a big difference. It has to be a ionic bond. All right. If I did fluorine with fluorine, oh, two big numbers, 4 minus 4, and this is true for any element, the difference is 0. It doesn't get any smaller than 0, so that's a pure covalent bond. That's the concept. Okay. So electronegativity is a known. We can actually do this math for any pair. And what we'll do is we'll figure out kind of some rough lines in the sand. What's the difference between covalent and polar covalent? What's the difference between polar covalent and ionic? There are certain differences which kind of make that borderline, if that makes sense. Okay, so, and here they are. All right, so these are a little fuzzy. Okay, it's not perfect science here. Okay, these are kind of ballpark numbers we use. Okay, so if I have a small electronegativity difference between 0 and 0.2, so if the numbers are within 0.2 of each other, we call that a covalent bond. The electrons are basically perfectly in the middle. If you go to the other end of the scale, we just did 3.3 is the biggest possible difference. So if the difference is 1.7 up to 3.3, that's technically a big number, a big difference in strength. That's going to be ionic. Anything that falls in the middle between 0.3 and 1.6 has character of both. It's polar covalent. Okay. So what I want you guys to do, and I'll fill this in, you know, as we progress here. Okay. Go back to this previous table. All right. Go to this previous table, or if you've got a textbook or even, you know, just the internet handy and you can find this online if you can't read the table. Just look at these numbers and work out the difference, and then use the scale and decide if it's covalent, polar covalent, or ionic. All right, so press pause, give it a shot. All right. Okay, so welcome back. Let's do, I'll keep mine on this side where I can see it, right? So I'm going to do H and Cl. Cl is 3.16. That's the big number. Hydrogen is 2.20 equals, get my trusty calculator, 3.16 minus 2.20 equals 0.96. 0.96, what kind of bond is that? Well, it fits nicely kind of in the middle of the polar covalent range, doesn't it? So we'll put PC. All right. Now, here's the thing. We can actually do it numerically, right? We can actually do it numerically, but on a test, you're not going to have access to this or the electronegativity number. So here's the, you know, the golden rule, right? If it's, we said it already, if it's a metal and a non-metal, it's definitely going to be a big difference. So it's going to be ionic. If it's molecular element, H plus H, F plus F, it's going to be pure covalent. Anything else is polar covalent. So what I want you guys to do, great if you worked out the numbers, right? But now just confirm it to yourself with just this simple logic, right? So, those guys there, Cl and Br, look at them in the data sheet here. 3.16, 2.96, 3.16 minus 2.96, 0.2. It's kind of right on the line. And you might say to yourself, well, what am I going to do here? Well, I'm actually going to say it's polar covalent because it's not two identical atoms. Okay. Obviously, that was a bad example because it's right on the line. But if we just use our simple relationships, we're good. This one, next one's nice and easy. Sodium fluoride. Well, it has to be ionic. If we do the numbers, fluorine, we go 4.0 minus sodium, 0.93. 3.07. Obviously way up there in the ionic range. Okay, if I bring that down, obviously way up there in the ionic range. All right. Now the next two, interesting, NO and CO. If we look at our map, we can see that as we get more towards the top right of the periodic table, they get stronger, right? Okay, so we can almost predict not just the bonding, but who's the stronger bond, right? In a way, all right? So, NO and CO, well, they're both non-metal and non-metal, okay? They're both different pairs, so they're both going to be polar covalent. But who's going to have the bigger difference in electronegativity, which will result in a stronger bond? And we'll talk about that trend later. Okay. Well, I'm going to predict that this one's strong. That this one's bigger, right? This one's bigger, and this one's smaller. Oh, let me get that. Let me just check that. Okay, I'm wrong prediction. I'm going to predict that this one is smaller and this one is bigger in terms of a difference, because if I go back to, let's just use a regular periodic table like you have on the test, right? Oxygen and carbon are further away than nitrogen and oxygen. So these are closer together. They'll have a smaller difference in strength. This is further apart. They'll have a bigger difference in strength. So I'm saying the CO bond has more of a difference in strength, which will result in more charge character, which makes it kind of stronger, which we'll see later. Okay. Look at the numbers. N and O. O is 3.44. I'll use that on both. Okay. N is 3.04. I think I can do that in my head. 0.40. All right. This one, carbon is 2.55. .89. So they're both in the polar covalent range, okay, between 0.3 and 1.6, which we expected, okay. But this one has more of a difference in electronegativity because the difference is bigger, okay. So CO difference is bigger than the NO difference, okay. Hope that's working for you, okay. Now, I have literally a minute left before the timer goes off. Remember, I run for 29 minutes before my camera automatically shuts off, all right? But I just introduced the concept, right? So in a little bit, our next thing, we'll talk about where that electronegativity number came from. It turns out that electronegativity was first devised by a very famous chemist called Linus Pauling, and that was in the when was that? Probably 1950s, early 1960s at the University of Chicago, actually. University of Chicago, well, local school, okay. And it's often called the Pauling scale of electronegativity. And he used probably 4 different atomic properties, which he put into an equation to calculate electronegativity, and the numbers are in the chart we just saw, okay? 2 of the things he used were size, or the radius of an atom, and first ionization. So those are the 2 we're going to look at for the course, but there are others we could use as well. If you take 101, we'll see those, okay? But we're going to look at the electronegativity trends and how they relate to the underlying trends, which are the same bottom left to top right for these 2 things. So again, these 2 things go into the calculation, and they have the same bottom left to top right kind of trend. Okay, see you in a minute.